Lighthouse Scientific Education presents a lecture in the mole series. The topic, molecular weight and conversions. Material in this lecture relies on an understanding of the previous lectures, the mole as a quantity, atomic mass and molecular weight, and dimensional analysis. The lecture begins with a brief review of the definitions and principles of molecular weight, formula weight, and molar mass. Then it is on to conversions between moles and mass and basic rules for these conversions. These rules are based on generating unit factors from the definition of molecular and formula weights. Several examples are shown. The last topic is a more complicated one. It is the conversion between number of particles and the mass of those particles. These are multiple step conversions that can be done as a single equation or using dimensional analysis. Four examples are given. To definitions. Molar mass is the mass of 1 mole of an element or compound. The units are grams per mole. In the previous lecture, it was shown that the mole is just a number, a counting unit. It is a very large number because atomic scale particles are very small. It is called Avogadro's number, and it is usually written in scientific notation. Often, just the first 3 numbers of the coefficient, 6.02, are used. Atomic mass is the molar mass of an element. It is the weight of a mole of an element, and it encompasses the different isotopes found in that element. Molecular weight, abbreviated MR or MW, is the sum of the atomic masses of a molecule or a polyatomic ion. It is very similar to molar mass, and the two terms are often interchanged. Molecular weight is the more commonly used term. Formula weight is the sum of the atomic masses from a formula. Molecular weight is a formula weight. Formula weight is a bit broader because it includes ionic compounds. In dealing with molecules, any of these 3 terms, molar mass, molecular weight, or formula weight, can be considered correct. Use the one that your instructor favors. We'll be favoring molecular weight. The first type of conversion covered in this lecture is the conversion between the mass and the moles. In that, molecular weight is a conversion factor. That also goes for molar mass and formula weight. Consider the molecular weight of H2O, 18.02 grams per mole. More explicitly, it can be written as 18.02 grams of H2O per 1 mole of H2O. That is to say, 18.02 grams of H2O is 1 mole of H2O. They are equal, and as such, when they are written in a ratio like molecular weight, they are a unit factor. Unit factors are covered in depth in the dimensional analysis lecture, and they are reviewed in the mole as a quantity lecture. The term unit means 1, and the ratio of 18.02 grams of H2O over 1 mole of H2O is equal to 1. Conversely, 1 mole of H2O over 18.02 grams of H2O is also 1. The two ratios are equal and can be used to convert between moles and grams, much in the way as the unit factor 12 inches over 1 foot can be used to convert a value in feet into an equivalent value in inches. Unit factors work because the starting units cancel out and leave a new unit. The math gives the numerical relationship between the values in the 2 units. Since 22.2 feet is equal to 266 inches, the unit factor must be equal to 1. There are a couple additional points that should be covered concerning molecular weight as a conversion factor. Most importantly is the use of the molecular weight in the correct orientation. This can be better understood by stepping back and evaluating a conversion from the perspective of units. A conversion will have a starting value with units. We will call those the current unit since the conversion has yet to happen. What those units will be converted into is called the desired units. The current and desired unit arrangement can also be termed the before units and the after units, before and after the conversion, or the have units and the want units. Each pair means the same thing. we will use the current and desired units. To get a correct conversion, the unit factor will need to have its current units oriented in such a manner that it cancels out with the units in the given or current value. In this setup, that means the unit factor has the current units in the denominator. Canceling out units is the single best way to prevent error in conversions. If units do not cancel, then try flipping the unit factor over and see if that works. We can use the unit factor from the molecular weight of water in an example of converting between mass and mole using the correct orientation of the molecular weight. Say that the current unit is in grams of water and the conversion is into moles of water. The correct orientation of the unit factor, the molecular weight, would have mass or grams in the denominator so that grams of water unit cancel out, leaving the unit moles of water. What if instead of grams for the current unit, we had moles of water and wanted to convert that into grams of water? The correct orientation of the unit factor would have a mole of water in the denominator so that moles would cancel out, leaving grams of water. Keep track of the units and conversions can become an important and useful tool in the study of chemistry. An outline of the basic process of conversions, including those using molecular weights, can be helpful in the beginning. The first thing that needs to be done is to identify the units involved in the conversion. For this discussion, we will leave the conversion to those between mass and moles. These steps work regardless of which of the unit types is given as the current units. Then identify the relationship between the units. For the conversion between mass and moles, that is the molecular or formula weight of the compound. Now set up an equation with current units on the left-hand side of the equal sign and desired units on the right. That provides the basis for making the correct choice for the orientation of the unit factor. Use the molecular weight to make a unit factor such that the current units will cancel out. What's left is to verify the correct orientation of the unit factor by canceling out units and then solve the numbers part of the equation with some calculator work. This is a straightforward process that will work every time if implemented correctly. Let's put it to work with a couple of examples. Beginning with, how many moles of H2O are there in 55 grams of H2O? The process begins by identifying what units are in the conversion. A review of the problem shows that we are given a mass of H2O and asked to convert that into moles. The conversion is grams to moles. What is the relationship between mass of water and moles of water? It is the molecular weight. Earlier we saw that it was 18.02 grams per mole. Begin the conversion with an equation that has the current units grams of water on the left of the equal sign and the desired units moles of water on the right of the equal sign. Using the relationship of molecular weight as a guide, orient the unit factor such that the current units, grams, cancel out. That will occur when grams are in the denominator. This is the flip of how molecular weight is usually written. Question: is it always the case that current unit will be in the bottom of the unit factor? No, not always. If the current units are themselves in the denominator, such as time units in velocity, think miles per hour, then the correct orientation of the unit factor would have the current units in the numerator of the unit factor. What drives the placement is the canceling of the current units. Here the orientation is correct because in the mass step, we cancel out current units of grams, leaving the desired units of moles. Taking the numbers to a calculator, 55 divided by 18.02 gives a conversion of 3.052 moles of H2O. There is one more consideration though. Our value in the current unit only has 2 digits or 2 significant figures. Since this is a multiplication problem, the rules say that our answer can only have 2 digits or 2 significant figures. The second significant figure in the answer is a 0. That digit is as far as this answer can be given. That doesn't mean we should just lop off the 5 and the 2. We need to consider whether the 0 needs to be rounded up. In this case, 0 does need to be rounded up to a 1, and our final answer is 3.1 moles of H2O. For a second example, we are given 2.55 moles of CO3 with a -2 charge and asked to find how many grams of carbonate. Identify the type of conversion. Moles of carbonate have been given and grams of carbonate have been asked for. This one is a conversion of moles into grams. The relationship between moles and grams is the molecular weight. The molecular weight of carbonate is 60.01 grams per mole. The process of getting the molecular weight is not shown here so that the focus remains on the current lesson. The next step is to set up an equation that has the current units or given units on the left-hand side and the desired or wanted units on the right-hand side. Success in correctly laying out the equation makes choosing the proper orientation of the unit factor straightforward. Look at the equation, and then look at the molecular weight of the carbonate. That molecular weight, as a conversion factor, needs to be oriented so that the given unit of moles cancel out. As currently written, the molecular weight has moles in the denominator. This allows the canceling out of the mole unit, leaving the desired gram units. A bit of multiplication and a value of 153.0 grams of carbonate is had. 2.55 moles of carbonate is 153.0 grams of carbonate. Are we done? Perhaps, but a check of significant figures is in order. Our starting value has 3 significant figures, meaning our final value cannot have more than 3 significant figures. The 3 is the third significant figure in our answer, so we need to consider whether we need to round that digit. Being followed by a 0, we should leave the 3 as it is, and our final answer is 153 grams of carbonate. A final example of a conversion with molecular weight starts with 97 grams of the sugar C6H12O6 and asks for the number of moles of C6H12O6. The conversion is one going from grams to moles. The relationship, as in the other examples, is the molecular weight of the sugar. If the student is still developing their skill in getting molecular weights, then perhaps they should pause the lecture, get out their periodic table, and give this molecule a try. On to the equation for the conversion. It has the starting value of 97 grams of the sugar as the current units on the left-hand side of the equation. Moles of C6H12O6 are on the right of the equal sign. Using the relationship of the molecular weight as a guide, insert a unit factor such that the current units of grams will cancel out. This orientation is another example of writing the flip of the molecular weight as the unit factor. In the math step, the student should always verify that the current units cancel out before getting out the calculator and doing the division problem. 97 divided by 180.16 gives a value of 0.584 moles of the sugar. A check of significant figures, and we're done. The starting value of 97 grams has 2 significant figures, so the converted value cannot have more than that. The 8 in the mole value is the second sig fig. It is followed by a 4, so we will not be rounding the 8 to a 9. 97 grams of the sugar, C6H12O6, is 0.58 moles of the sugar. As with many of the processes involved in the study of chemistry, it is absolutely to the student's benefit to develop a strategy and to rigorously apply it in all circumstances. That will be especially true of the last topic of this lecture, conversion between particles and mass, because there is no direct conversion between the number of particles and grams of particles. While that's not exactly true, the process described here is significantly easier. In this type of conversion, we will see that the mole plays the intermediate between the very large numbers associated with atomic scale particles and the mass of those particles. To be more specific, we are considering the conversion between a count, or number of particles, that goes through two conversions to get mass, as in grams, of those particles. One of the conversions was covered in the mole as a quantity lecture, and the other was a topic of this lecture. That is, the first conversion goes from number of particles into moles of particles. In the mole as a quantity lecture, going from the number of particles to moles of particles is done using a unit factor from the definition of moles. 1 mole of particles equals 6.022 times 10 to the 23rd particles. That's Avogadro's number. The second conversion takes the newly found unit of moles and, with the appropriate unit factor, converts it into mass. That unit factor is the one we just covered in this lecture. It is the molecular weight of the particle. So this overall conversion uses moles twice. Each of the unit factors will have moles in them. Moles are useful in handling quantities in chemistry. They may initially seem burdensome. An analogy would be having to do all math with numbers in terms of dozens. That would mean that each individual number would have to be initially converted into dozens, some math would be done on the dozens, and then the answer would be converted back out of dozens into regular numbers. Burdensome. So while working in moles has this same labor, once mastered, the mole shows itself as an indispensable tool. That might just have to be taken on faith. From here on in, we are in the world of moles, and this common refrain will be used again and again. Get into moles, get out of moles. To be complete, we should ask if two conversions are necessary when starting with grams of particles and asking for count of particles. Yes, they are, and they will also go through moles of particles. In this situation, the first conversion, mass to moles, will use a molecular weight unit factor, and the second conversion will use the unit factor with Avogadro's number. These conversions are really just the reverse of the conversions that started with number of particles. The unit factors are the flips or reciprocals. That same refrain of getting into moles and then getting out of moles is used. The two conversions can be done separately or combined into a multiple-step dimensional analysis equation. We will cover 4 examples and do so using both ways with the first 3. The last example we've done with just dimensional analysis. Our first conversion asks us to find how many moles of H2O molecules are there in 25 grams of H2O. The overall conversion is going from mass, grams of particles, to numbers of particles, with molecules being the particles. Since we do not have a direct conversion between these units, we need more than one conversion. We will need 2 conversions to be exact. Fortunately, we have our refrain to help us along. The first conversion will be to get into moles, and the second will be to get out of moles and into number of molecules. These conversions can be done one after the other. Use the result of the first conversion as the start of the second, or with one multiple-step equation. We will first do the problem as individual conversions. Starting with the first conversion, and using the same steps that we used earlier in the lecture. Identify the type of conversion. It is mass, 25 grams, converted into moles of particles, molecules. The relationship between mass and moles of particles is the molecular weight of H2O. 1 mole of H2O is 18.02 grams of H2O. Now, set up an equation that relates current units to desired units. The current unit is grams of water, given our 25 grams of water, which is equal to some amount of moles of water. With this setup, determine the correct unit factor. Success in this step is found by arranging the molecular weight so that the unit grams cancel out. This will be the case if grams are in the denominator. We see that this unit factor is the reciprocal or the flip of the molecular weight from the relationship step. It is not as simple as inputting the relationship. The correct arrangement of units in the denominator and in the numerator also has to be considered. Moving on to the math step and canceling out grams of water, leaving moles of water, and just a bit of arithmetic. 25 divided by 18.02 yields the answer of 1.39 moles of water. 25 grams is 1.39 moles of water. Since we're going to use that 1.39 value in another calculation, we should hold off checking significant figures. That is done just once and always at the end. Before the start of the second calculation, a minor modification to the original question can be made that prepares us for the next calculation. Without altering the value in the problem, the 25 grams can be replaced with an equal value of 1.39 moles. Now the second calculation, getting out of moles, looks like a conversion we covered before. First, identify the type of conversion at hand. It is those 1.39 moles into particles. Is there a known relationship between moles and number of particles? From the introductory lecture on moles, we see that it is the definition of a mole. 1 mole equals Avogadro's number, and as written here, is a unit factor. Writing out the equation has us adding the current units on the left, 1.39 moles, and the desired units? Right, molecules of water, on the right-hand side. The correct orientation of the unit factor will have the moles in the denominator so that they cancel out. It is already in that orientation. Be sure to include the water along with the numbers and the units in the unit factor. The current units, by the way, do cancel out in the math step. The multiplication of 1.39 times 6.02 times 10 to the 23rd will give a value of 8.37 times 10 to the 23rd molecules of water. That is how many water molecules are in 1.39 moles, or 25 grams of water. What's left is a check of sig figs. From the original problem, it can be seen that the given value of 25 only has 2 sig figs. That means the answer cannot have more than 2 sig figs. That 3 is in the last position of the final answer. Does that 7 that follows the 3 mean that the 3 is moved up to a 4, or should it stay as a 3? Since 7 is greater than or equal to 5, the 3 is rounded to a 4, and the final answer, or the final answer, is 8.4 times 10 to the 23rd molecules of water. This problem was solved in 2 separate conversions. It can also be solved by combining those 2 separate conversions into a single equation in a process called dimensional analysis. This process is covered in depth in its own lecture in the Measurement and Number series. It is essentially the same set of steps used in the 2 conversions, which are gathered in the lower rectangle on the screen. There is one additional understanding, though, and we will get to that. The dimensional analysis equation begins by identifying the overall conversion. The given or the current value is the grams of H2O. That will be converted into moles of H2O, which will then be converted into desired units of molecules of H2O. Dimensional analysis has us solve individual conversions in order, one at a time, moving left to right. The first conversion is the grams to mole conversion, and the logic and the look is exactly like the first of the single conversions already solved below. In that conversion, the unit factor of molecular weight is added to the equation. A slight change in syntax is also shown. Instead of a multiplication sign followed by the unit factor, a set of parentheses with the unit factor inside is used. It is the same thing, since a value directly in front of parentheses is multiplied by what is in the parentheses. As such, the unit grams of water cancel out, just like they did in the first of the 2 individual conversions. Doing the division in the conversion would, of course, give us the same 1.39 moles of water. However, in a dimensional analysis equation, doing the math is held off until the entire set of conversions is complete. So far, these are identical equations. The additional understanding in the dimensional analysis is that the equation we have so far is also equal to the starting value of the second conversion. They are all 1.39 moles of water. This means we can leave the dimensional equation as is, but treat it as if it was the start of the second equation, which means it is time to get out of moles, and that is done by adding in the same unit factor used in the second conversion. It is inserted in line next to the first unit factor. Yes, parentheses are added. Note that the moles of water cancel out, got out of moles, leaving the units of molecules of water. This equation is complete with the exception of the math. And the math is more complex with dimensional analysis. A calculator hint with this math would be to do all the multiplications first, 25 times 6.02 times 10 to the 23rd, and then do all the divisions. Divide by 18.02. Multiplying or dividing by 1 does not change the value, so the ones can be omitted in the calculation. The result should be 8.4 times 10 to the 23rd molecules. Both methods produce the same result, and either way can be used. Be forewarned, though, that when the difficult subject of stoichiometry comes up, having practiced dimensional analysis with getting into moles and getting out of moles will greatly reduce the initial confusion of that topic. One last point concerning dimensional analysis. Here we use parentheses to hold the unit factors. Some teachers do not use parentheses to teach dimensional analysis. Instead, they use a grid where all the numerators and non-fractions are in the top row and all the denominators in the bottom row. It makes the crossing out of units easier, but in every other way, it is identical to the process covered here. That was a lot to take in, so we should try a few more examples to solidify our understanding. Our second example asks, how many grams of CO3 minus 2 carbonate are there in 1.00 times 10 to the 24th particles, ions, of carbonate? Identification of such problems as conversion problems should become easier with each new problem. The given or current value of the overall conversion is the number of particles. What it asks for is mass. What might take a while to master with conversions is gauging which type of conversion can be done with one unit factor and which require more than one. The number to mass conversion is of the later type. This conversion will require the mole, that is, get into moles from particles and then get out of moles into mass. It is a two conversion problem, and we will do them individually before combining them into a single dimensional analysis equation. Starting with the first conversion. Identify the type of conversion. It is number of particles going into moles. What is the relationship between number of particles and moles of particles? Yes, the definition of the mole. 1 mole is the number 6.02 times 10 to the 23rd. Return to the question and write down the outline of the equation of the specific conversion. The number of particles is on the left-hand side and the number of moles is on the right. It may be tempting to write grams of particles as the desired unit, but this is a multiple part conversion problem and getting grams is not the current focus. The single most important factor in getting the problem right is the correct assignment of units. Choosing a unit factor has us using the relationship with an orientation that cancels out the given units of particles of ions. That is 1 mole of carbonate ions over 6.02 times 10 to the 23rd carbonate ions. In the math step, the correct orientation of the unit factor is verified with the canceling out of units. Dividing takes a knowledge of one's calculator, especially in handling the exponent. The answer should be a value of 1.66. Clearly an easier number to deal with than 1 times 10 to the 24th, which is exactly why we use the mole. Again, we will wait until all the math is done before checking sig figs. While it is not necessary, we can return to the problem and update it with the equivalent amount of moles. On to the second conversion, getting out of moles, and we will be using this 1.66 moles. Let's specifically identify the conversion of interest. We have moles, and we want mass in grams. That relationship between moles of a substance and the mass of that substance is the molecular weight. 60.01 grams of carbonate is 1 mole of carbonate. An equation of the conversion will start with the solution to the previous problem, 1.66 moles of carbonate. It is our current unit in the second conversion. The desired units are what the problem asks for, grams of carbonate. Almost there. We need the correct unit factor as outlined in the relationship step. Moles of carbonate need to cancel out, so the molecular weight, as written, will be correct. Do the units cancel out? Yes, they do. And a more reasonable math problem awaits with a final value of 99.7 grams of carbonate. A final check of sig figs has us return to the original given value with its 3 sig figs. Remember, exponents play no role in significant figures. 3 sig figs is also what the final answer has, so no change is needed. The two conversions can be combined into a single-dimensional analysis equation. In considering the conversion as a whole, the given or current units is the number of particles, ions. The wanted or desired units is the mass in the form of grams. Bringing up the individual conversions will show that the dimensional analysis is really just the combination of the two equations. The logic of the dimensional analysis equation is the same logic. We do not have a direct conversion from count to mass, so we will need to go through moles. The first conversion is the template for the start of the dimensional analysis equation. They both have count of carbonate as a current unit, and they both use the relationship of 1 mole of carbonate to Avogadro's number of carbonate ions. Units cancel out, and so far these two equations are identical. That is, with the exception of the parentheses. As such, they yield the same 1.66 moles of carbonate. That is also the starting value of the second conversion. The dimensional analysis equation as currently written is essentially the same thing. That means we can leave it as it is and proceed with getting out of moles. The intellectual leap in moving from individual conversions to dimensional analysis is recognizing what the current units and what the desired units are for the particular conversion. The current units at this particular juncture in the equation are the moles, since the count of carbonate has canceled out. The correct unit factor between moles and the desired units, grams, is the molecular weight of carbonate, just like it is in the second conversion. Units of moles of carbonate cancel out, leaving grams of carbonate, and multiplying all numerators together and dividing by all the denominators gives 99.7 grams of carbonate. Both the dimensional analysis and the two separate conversions give the same results. On to example 3. 15 grams of carbon is how many carbon atoms? Identification of the overall conversion is one of grams of particles atoms into number of count of particles. Since we do not have a relationship between these units, it falls on us to build a bridge between them, and that bridge is the mole. Getting into moles, getting out of moles. The overall logic of the problem is set. Solving the problem in separate equations begins by identifying the type of the first conversion. It is mass of carbon into moles of carbon. What relationship is there between these units? Well, carbon is an element, so atomic molar mass is the relationship. A quick survey of the periodic table shows the atomic molar mass of carbon to be 12.01 grams per mole. The relationship is therefore 12.01 grams of carbon being equal to 1 mole of carbon. Setting up an equation has the 15 grams of carbon as the current unit on the left-hand side and moles of carbon on the right. Selecting the correct orientation of the unit factor, atomic molar mass, is a matter of having the unit grams in position to cancel out. That requires a flip of the atomic molar mass so that the grams are in the denominator. The mass step verifies our correct choice by canceling out gram units. 15 divided by 12.01 gives a value of 1.25. 15 grams of carbon is 1.25 moles of carbon. Holding off on the check of sig figs and moving into the second conversion, getting out of moles, the 1.25 moles of carbon stays and will be the new current unit. This second conversion is identified as going from moles to count. The relationship between those units is the definition of moles with Avogadro's number of particles. The equation in this conversion takes the solution of the previous conversion as the current value of this conversion. The number of carbon atoms is the desired unit. The orientation of the relationship that makes an appropriate unit factor will have the unit of moles in the denominator so that in the mass step the current unit cancels out, leaving count of atoms. Multiplication of 1.25 times Avogadro's number divided by 1 produces a value of 7.52 times 10 to the 23rd. That is how many carbon atoms there are in 15 grams of carbon. Speaking of 15 grams, there are only 2 significant figures in that value, so the final solution cannot have more than 2 significant figures. The 5 occupies the second position. Being followed by a 2, there will be no rounding up, and the proper solution to the problem is 7.5 times 10 to the 23rd carbon atoms. To continue the practice of dimensional analysis, we will repeat the conversion of 15 grams of carbon into count of carbon atoms. We do not have a direct conversion from mass to count, and that means there will be more than one conversion in the dimensional analysis. The single conversions are included to give perspective. The getting into moles conversion in the dimensional analysis follows the same steps that were used in the first individual conversion. Units are identified, a relationship is established, and the correct orientation of the unit factor is inserted. Hopefully, it will look like this. That unit grams cancels out is a good sign that we got it right. And once again, we see that the start of the dimensional analysis looks just like the first conversion. They both equal 1.25 moles of carbon. Since that is also the start of the second conversion, the second part of the dimensional analysis, getting out of moles, will look just like the second conversion, including the unit factor, the atomic molar mass of carbon. Mole units cancel out, and 15 times 6.02 times 10 to the 23rd divided by 12.01 produces 7.5 times 10 to the 23rd carbon atoms, as was seen in the second conversion. That is 3 examples of doing the count to mass conversion as single conversions and using dimensional analysis. The last example will be done solely as a dimensional analysis equation. What is the mass of 2.3 times 10 to the 25th calcium ions, Ca plus 2? Identification of the overall process has the given units as number of particles, ions, and the desired units in mass, grams. Without a direct conversion, the process will almost certainly go through moles. Getting into moles, getting out of moles. The logic of this conversion is the same as the previous 3 examples. A 2-part conversion using dimensional analysis will look very similar to doing the conversions in separate equations. The main differences are that the current unit and the desired units change as the equation proceeds, and the math is held off to the end. Including the specifics in the overall equation has the count of ions as the initial current unit and the grams of calcium ion as the final desired unit. While our solution will be in the form of a dimensional analysis equation, The first of the multiple conversions should be addressed as if it were a single conversion. Identify the units in the conversion. A big step in mastering the dimensional analysis technique is correctly identifying what units are in the conversion at hand. In a multiple step conversions, they will never be both the current units and the desired units as given in the problem. In this conversion, it does use given units in the problem as the current unit, but the desired units are not grams of calcium. They are the objective of the specific conversion. They are, in this case, moles of calcium ion. Correctly identifying the units, especially when one unit type is currently not written in the equation, is a difficult step, but once it has been made, the conversion moves on into establishing a relationship between the count of ions and the number of moles of the ion. And that relationship is the definition of mole, Avogadro's number, over 1 mole. If an equation has not been set up with current units of count, then do so. However, the desired units of moles are not written in the equation. This is one of the ways a single conversion differs from a multiple step conversion. The desired units will be brought in, but they will get in as part of the correct unit factor. The orientation of the unit factor, as found in the relationship step, needs to be one that has count in the denominator and moles in the numerator, like this. Remember to include the calcium ion information. Another difference in the dimensional analysis approach is the mass step. Unless this particular conversion is the last conversion, hold off on the math. That doesn't mean that units should not be canceled out. That is how we verify the correct orientation of the unit factor. Canceling also shows that we end up with units of moles. The first conversion is complete, and it is now time to get out of moles. The second conversion repeats the steps of the single conversion. Begin by identifying the conversion. It starts with the units remaining from the first conversion, moles, and goes to the final desired units of mass in the form of grams. The relationship between moles of ion and grams of ions is the atomic molar mass. Ions, to a large degree, have the same atomic molar mass as their atoms do. The periodic table shows the element calcium to have an atomic molar mass of 40.08 grams per mole. 40.08 grams of the calcium ion is 1 mole of calcium ion. And what should be done about the equation? It already has current and desired units, so nothing more is required. All that remains to complete the dimensional analysis equation is the unit factor that converts moles into grams. The atomic molar mass, as written in the relationship, will do, since in the mass step, moles cancel out. The remaining unit is grams, which tells us that the problem was set up correctly. The calcular math can be a bit daunting, but as mentioned earlier, a good practice in solving these equations with multiple multiplications and divisions is to do all the multiplications first, and then all the divisions. Additionally, the multiplication and division of ones can be skipped. So, the calculation would follow as 2.3 times 10 to the 25th times 40.08 divided by 6.02 times 10 to the 23rd. That gives 1,531 grams of calcium ion. All that is left is a check of sig figs. The given value of 2.3 has 3 sig figs. The solution to the problem has the third sig fig being a 3. Since it is followed by a 1, there is no need to round up. It stays a 3, and the correct answer to the problem is 1,530. Yes, there's the fourth digit here, but it does not carry significance. It is needed because removing it would leave 153, which is not the right answer. Develop dimensional analysis as a tool, and it will reward you all the way through your studies. To recap the lecture, molar mass is the mass of 1 mole of an element or compound. The units are grams per mole. Molecular weight is a conversion factor. It is a unit factor since numerator equals denominator. There are convenient steps for converting between mass and moles. These steps can also be used for other conversions. Begin by identifying the units involved in the conversion. Get a relationship. For the mole-mass conversion, that is the molecular weight of the compound. Next, set up an equation, current units on the left, desired units on the right. Make a unit factor from the relationship such that the current units will cancel out. Cancel out the units and solve the math. Not all conversions can be done with a single unit factor, though. There is no direct conversion between number of particles and grams of particles. There is an intermediate, and it is the mole. A common refrain in chemistry when dealing with mass is getting into moles and then getting out of moles. This helps us remember that the mole bridges the units of count and mass. The two-step conversion can be from count of particles through moles into mass, or the other way around, starting with mass of particles that convert into moles, allowing a final conversion into particles. And that concludes our lecture. The best advice for this material is to practice, 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 and watch and cancel your units.